Hello everyone, my name is Memon from the University of Science and Technology of China. Today the topic of my presentation is the design of high Q film bulk acoustic resonator for 5G application. This is the outline of the presentation in which I will be covering the introduction, the problem and the optimization techniques, some results and discussion, conclusion and reference. Why we need the acoustic resonator as the increasing demand of the filters in a smartphone from 2014 to 2018 it was around 40 to 60 but till 2022 it is expected that it will be more than 90. So in a smartphone or a smart devices we will be having more than 90 filters uh, for the for the communication system inside the cell phone. So the global market of bulk acoustic wave resonator is around 3070 million, and it will be increasing with the increase of the technology, the communication technology such as 4G, 5G, and 6G in the future. So why we need FBAR? As we know that FBAR is a key technology which is being used in the 4G and 5G communication systems, and it has low insertion losses. It has stripper filtering, better out of band rejection, and ultra small size devices, and it has low insertion losses, which is obviously affect it will obviously affect the battery life of the device. So the importance of the film bulk acoustic resonator is, as you can see in the graphical representation, that above 3.5 gigahertz, okay, till 5.5 gigahertz, the bulk acoustic resonator has higher performance regardless of the other resonators, which are the conventional resonators or filters. So the frequency below the frequency above 2 gigahertz, the BAW filter is preferred. So where we can use the F bar, the filter, in the wireless communication system, as this is the simplest wireless communication system. So the filter can be used in the band pass before the low noise amplifier for between the transceiver and antenna. So an efficient and optimized design is required, which can use as an efficient filter. Obviously, if we have the high quality factor, if we have high Q, so obviously the filter which we use to design using the FBAR method, FBAR technology. So it will have higher. So what are the requirements of 5G, or we can say sub 6G, which is already being used in today's communication system? So 5G has been introduced recently in 2020, which is also called as sub 6G. So we need an high quality and efficient electromechanical coupling are required for sub 6G. So this is the fundamental analysis of FBAR. So we have a piezoelectric film, and then it is sandwiched by the electrode, and when the electrical potential is applied, the mechanical energy is converted into electrical energy and vice versa. And this is the ideal frequency response, and this is the MBVD model, which is considered as the equivalent model of that device. And this is the animation which shows the resonating path of the film, piezoelectric film, in a slow motion. So higher the resonating frequency, higher the bandwidth will be. So there's a performance factor, how we can evaluate the performance factor of F bar. These are the formulas, these are the equations which you use to extract out the quality factors. We have the resonant frequency, and we have the anti-resonant frequency, and the electromechanical coupling. So the performance of the device is of the acoustic resonator depends on the electromechanical coupling and the quality factors, and these are considered as the key factors uh, to just evaluate the performance of the. So what problems we have? So we have the problem of acoustic leakage. the source of leakage caused due to the transition of stress level from the active region. This is the active region, and it goes outside the active region. This is considered an active region in which the piezoelectric is between the electrodes. So it degrades the quality factor. What happened that when the leakage is more, so it will minimize the quality factor, and also the electromechanical coupling. So when we see an unoptimized design, so we can say that the graphical representation, that the impedance, we have this kind of noise between the filter and this kind of noise, which is called as spurious resonances, and it can be also seen in the Smith chart. So the occurrence of spurious resonances uh, degrades the performance of the resonator, obviously degrades the performance of the resonator. So previously design was the simulated work. Again, what kind of optimization technique we can utilize to minimize the spurious resonance? Number one is you utilizing the apodization techniques, which is being used, and other is age loading or raise frame techniques. So we will be implementing both of the techniques to minimize the losses. Uh, in this, we have utilized the on-scale cloud computing finite element analysis method, in which aluminum nitride is used as a piezoelectric material. It has some features to the current high gigahertz frequency, and we will be using a silicon nitride as a support layer. The losses which we have included as a as in the simulation, we need to add some losses, because when we do the device fabrication, so the losses are obviously included. So a cheaper and a faster representation is required before the fabrication. So we just do the simulation to minimize the cost of the fabrication, which we have utilized. This is the three-step high quality factor for 5G application. This is the design of a high Q design, and that design can be used for sub-G gigahertz. Let's see the using the parametric optimization. We have simulated the three-step design as utilizing the edge putting technology at the edges of the electrode, and we have obtained a high quality factor, and these are the some parameters of the device, the thickness and the uh, results and discussion. First, we have utilized the apodized technique. So these are the results. This is the displacement comparison. As you can see that there is an acoustic leakage outside the active region. The active region, again I'm repeating that active region is the one in which the piezoelectric material is sandwiched between by the electrodes. So in the apodized, the displacement has been minimized, and further we can see that the comparison, the apodization techniques and its comparison, as you can see that the simple F bar design has more loss, okay, rather than the hexahedron, but this does not minimize the spurious resonances completely. So implementing the three-step design, as you can see, utilizing the three-step design, we have minimized the losses, and you can see that the smoother bandwidth has been achieved. And in the Smith chart, we can also see that the unwanted resonance or minimum error has been achieved. And this are the obtained results, which has the 4 gigahertz as resonant frequency and anti-resonant frequency of 4.14 gigahertz, having the high quality factor with efficient electromechanical coupling. This is the displacement distribution in 2D. And this is the MBVD model. We have compared our designed results, and it shows good agreement with MBVD model. These are the extracted parameters, and this is the equivalence. So this work has already been published in MTTS IWS IEEE conference, and it has this design proves more efficient in terms of performance. This is the comparison. conclusion that we have a apodization technique does not minimize the spurious mode efficiently, but yeah, it obviously minimize. So the three-step design is the competent design with the declining steps, and it has a high quality factor, a high electromechanical coupling, and the proposed design has highly useful for filters and other RF applications. Uh, these are the references. Thank you so much. Thanks.